Our solar system is not the quiet neighborhood we think it is. It is a place of profound and unsettling mysteries, hidden in plain sight. This journey will reveal 25 cosmic secrets that defy our current science, transforming how you see our corner of the universe. We will explore a world with a hurricane that never dies and a silent giant that may be hiding in the dark. You will discover how much we truly have yet to learn. What is the strangest thing you believe is waiting to be found out there? Venus presents a paradox that defies our earthly intuition. A single day there, the time it takes for the planet to complete one full rotation on its axis, lasts longer than an entire Venusian year. Yet high above its scorching surface, the entire atmosphere is caught in a frenzy, whipping around the globe at hundreds of miles per hour. These hurricane-force winds in the upper cloud decks complete a full circuit of the planet in just 4 Earth days, a phenomenon scientists call superrotation. Imagine the entire sky of Earth moving as one solid, raging river, circling our planet faster than we could ever hope to fly. This is the permanent state of Venus. The energy required to sustain such a planet-wide atmospheric jet is staggering, and while theories point to the sun's intense heat creating thermal tides and transferring momentum, no model fully accounts for the sheer violence of this perpetual motion. It is as if the atmosphere has become unshackled from the planet itself, operating by a separate set of rules we do not yet understand. This mystery forces a fundamental rethink of planetary fluid dynamics, challenging our assumptions about how weather and climate function on a global scale. What hidden engine, buried within the interactions of solar radiation and those thick, acidic clouds, drives this supersonic weather machine? Solving it would not only explain Venus, it could reveal entirely new principles of atmospheric physics, showing us that even the basic forces shaping a world can hold profound and unexpected secrets. Yet the strangest storm in the solar system is not a vortex of fire or wind, but a shape. At Saturn's North Pole, a perfect 6-sided hexagon, a geometric wonder carved from clouds, has been spinning for at least 4 decades. This is not an artist's impression or a trick of the light. It is a persistent jet stream, a hurricane with 6 razor-straight sides, each longer than the entire Earth is wide. You could fit 4 of our planet inside this colossal atmospheric polygon, a structure so precise it looks engineered. While laboratory experiments with spinning fluids can produce similar geometric shapes, scaling that phenomenon to the atmosphere of a gas giant, with its unimaginable pressures, complex chemistry, and deep internal heat, presents a puzzle our best weather models cannot fully solve. The hexagon's stability is as baffling as its form, enduring through Saturn's long seasons without distorting. Scientists suspect it may be the visible crest of a deep-seated atmospheric wave, a standing pattern created by the interaction between different layers of the planet's churning interior and its rapid rotation, perhaps even influenced by Saturn's powerful magnetic field. This celestial artifact, first glimpsed by Voyager and later studied in stunning detail by Cassini, is more than a curiosity. It is a stark declaration that the atmospheres of gas giants operate under a physics we are only beginning to glimpse, where fluid dynamics on a planetary scale can produce architecture. If a simple rotating fluid in a lab can create a hexagon, what other impossible shapes might be waiting, hidden in the swirling depths of Jupiter or the icy winds of Neptune? This geometric storm guides our curiosity outward, challenging us to look at every giant planet not as a simple sphere of gas, but as a canvas for meteorological art we have yet to comprehend. But for all the grandeur of planetary storms, the most unsettling mysteries can arrive without warning from the void. On a quiet summer morning in June of 1908, over a remote Siberian forest near the Tunguska River, the sky tore itself apart. A flash brighter than the sun was followed by a shockwave that leveled 800 square miles of ancient trees, snapping them like matchsticks in a perfect radial pattern. The force was 1,000 times greater than the atomic bomb dropped on Hiroshima decades later, yet when investigators finally reached the epicenter years after, they found no crater. The ground was scorched and littered with fallen giants, but there was no hole, no smoking pit where a space rock should have buried itself. This is the enduring puzzle of the Tunguska Event. The leading explanation is a stony asteroid, perhaps the size of a small building, that exploded in a blinding fireball several miles above the Earth, its energy dissipating in the atmosphere before any solid remnant could strike the ground. It was a natural airburst of unimaginable power, yet the frustrating lack of definitive meteorite fragments, the kind of iron or stone evidence we can hold, has kept the door open for more exotic ideas over the decades. Could it have been a fragment of a comet made more of ice and dust that vaporized completely? Some have even speculated, though with little supporting evidence, about a passing microscopic black hole or a chunk of antimatter annihilating on contact with our atmosphere. More recently, sophisticated simulations suggest another fascinating possibility, a cosmic ricochet. Imagine the object not as a direct plunge, but as a shallow, glancing blow. It could have skimmed the upper atmosphere like a stone skipping on a pond, heating, fragmenting, and finally detonating in a terminal flash before arcing back out into space, leaving only its explosive energy as a calling card. This mystery is far more than a historical curiosity. It underscores a sobering vulnerability. Our planet sails through a solar system littered with small, dark, and difficult-to-track objects. Tunguska was a wake-up call to a force that had shaped our world's history long before human civilization, from the dinosaur-ending impact to countless smaller events lost to time. It highlights critical gaps in our understanding, not just of what these objects are made of, but of how they behave during that final, fiery interaction with our protective blanket of air. Will the next one be another airburst over an ocean or an unpopulated forest? Or will its timing and trajectory tell a different story? The silent lesson of Tunguska connects directly to the active and urgent puzzle of near-Earth object dynamics, a reminder that some of the solar system's deepest secrets are not just out there, but on a path that occasionally intersects our own. While Tunguska reminds us of impacts from the outside, one world in our family bears the permanent signature of a collision from within. Uranus spins on its side. This is not a slight tilt like Earth's, which gives us our gentle seasons. This is a planetary cartwheel. Imagine rolling a bowling ball down the lane, its axis of spin pointing straight ahead. Now picture every other planet in the solar system spinning upright like a top. Uranus alone rolls along its orbital path, with its north pole pointed almost directly at the Sun during part of its long year. This bizarre orientation creates the most extreme seasons imaginable. For 42 Earth years, one pole basks in continuous sunlight, a day that lasts for decades, while the other pole is plunged into a frigid 42-year-long night. Then, as Uranus continues its 84-year journey around the Sun, the roles slowly reverse. The entire climate of the planet, what little atmosphere it has, must churn under this staggering imbalance of solar heating. The leading explanation for this cosmic tumble is as violent as it is simple, a cataclysmic collision in the solar system's youth. Theorists propose an early Uranus, still forming, was struck a glancing blow by a protoplanet roughly the size of Earth. Such an unimaginable impact could have literally knocked the world onto its side, forever altering its rotation. Yet, as with all good mysteries, the evidence is not so clear-cut. A collision of that magnitude should have left other forensic clues. It might have drastically reshaped the planet's interior, affecting the generation of its magnetic field, which is oddly offset and tilted from the planet's center. It could have scattered material to form rings and moons with unique compositions. While some of Uranus's moons do orbit in that same tilted plane, suggesting they formed from the debris of such an event, other signatures do not perfectly match the collision model. This discrepancy has given rise to an alternative and perhaps even more fascinating idea. What if Uranus was not pushed but pulled during the early chaotic dance of the giant planets as they migrated to their current orbits? Gravitational tugs from Jupiter and Saturn could have exerted a gradual, persistent torque on the young Uranus. Over millions of years, these resonant pulls might have slowly, inexorably tilted the entire world, like a spinning top gradually wobbling over until it lies on its side. This gentler mechanism avoids some of the physical inconsistencies of a single shattering impact, but it adds profound complexity to our models of planetary migration. It suggests the early solar system was not a placid nursery, but a gravitational pinball machine where worlds could be fundamentally reoriented by invisible forces over cosmic timescales. The sideways roll of Uranus, therefore, is more than a planetary oddity. It is a frozen question mark in the history of our neighborhood. Was it a sudden, violent accident or the slow, inevitable result of gravitational whispers? Answering this forces us to reconsider the very narrative of how planetary systems settle into their final arrangements, and it pushes astronomers to look for similar tilted giants around other stars, searching for clues to whether our solar system's story is common or a unique tale written in a sideways spin. The search for life often begins with a single molecule, and on Mars, that molecule is methane. Sporadic plumes of this simple gas have been detected by our robotic emissaries, whispering through the planet's thin, cold air before vanishing without a trace. This is a profound chemical mystery, for methane on Mars should not last. The relentless barrage of solar ultraviolet radiation breaks it apart rapidly, meaning any methane we detect must have been released very recently. On our own world, methane is a vibrant signature of activity. It burbles from wetlands, escapes from livestock, and seeps from geological processes deep within the Earth. Its presence is so often tied to life that finding it on another planet sends an undeniable thrill of possibility through the scientific community. Could these fleeting Martian whiffs be the metabolic byproduct of tiny, resilient microbes surviving in briny pockets of water deep beneath the frozen regolith? It is a hypothesis that captures the imagination, suggesting a second genesis of life right next door. Yet the cosmos is careful not to give up its secrets so easily. There are non-biological explanations that are equally compelling. A process called serpentinization, where certain rocks react with water deep underground, can produce methane through pure geology. Ancient deposits of methane ice, called clathrates, could be trapped in the polar caps, releasing their store in sudden, unpredictable bursts when the temperature or pressure shifts. Even organic material delivered by countless meteorites over billions of years could be breaking down under the Martian surface, slowly leaking this enigmatic gas. The true frustration lies in the signal's elusiveness. The plumes appear in one location, detected by a rover's sensitive instruments or an orbiter's spectral eye, and then they are gone. By the time follow-up observations are made, the atmospheric clue has dissipated, leaving scientists to piece together a crime scene where the evidence has already vanished. This intermittent nature makes pinpointing the source nearly impossible with our current tools. Is it a single, localized vent or a diffuse process happening across the planet? The answer holds the key to understanding whether Mars is a geologically active world with a hidden, wet interior or something far more profound. This search for a methane source is not an isolated puzzle. It is the central thread in the grandest investigation of all, the quest to determine if we are alone. Every unexplained flicker in the Martian atmosphere pulls us deeper into the mystery of what, or who our cosmic neighbors might be. Far from the arid plains of Mars, another world offers its secrets not in whispers but in glorious, eruptive shouts. Enceladus, a small, brilliant moon of Saturn, is actively firing immense geysers of water vapor and ice crystals hundreds of miles into space. These dazzling plumes, erupting from deep fractures nicknamed tiger stripes near its south pole, are so prolific they feed one of Saturn's faint outer rings, a halo of ice created by this tiny moon's continuous cryovolcanic breath. For years, this was seen as a spectacular but distant curiosity. Then the Cassini spacecraft flew through the Plumes, and our understanding of this icy world shattered. The spray was not just water ice, it was a complex cocktail containing simple organic molecules, the carbon-based building blocks of life, and perhaps most tantalizing, molecular hydrogen. This hydrogen is the chemical equivalent of a blinking neon sign. On Earth, molecular hydrogen streaming from the seafloor is a telltale signature of hydrothermal vents, where superheated water reacts with rock in the eternal darkness of the deep ocean. Around these vents, in complete absence of sunlight, thriving ecosystems draw their energy not from the sun, but from chemistry. The discovery suggests Enceladus possesses a global, salty subsurface ocean, kept liquid not by the distant sun's weak warmth, but by the gravitational kneading of Saturn. As the moon orbits, Saturn's immense pull flexes its icy shell, generating internal heat through tidal friction. This heat warms the ocean and likely drives hydrothermal activity on the rocky seafloor far below the ice. Here, in perpetual night, water interacts with a hot, mineral-rich core, creating the perfect conditions for chemistry to become biology. Enceladus, therefore, is no longer just a moon. It is a sealed bottle shaken by a giant's hand, with a label that lists every essential ingredient for life as we know it: liquid water, chemical building blocks, and a persistent source of energy. We have, in our own solar system, a world with a hidden sea potentially more voluminous than all of Earth's oceans combined, and that sea may be churning with the same processes that gave rise to life in our planet's deepest, darkest abyss. This transforms a pinprick of light orbiting Saturn into arguably the single most compelling location to search for extraterrestrial life. It forces a profound and humbling question: if the recipe for life is so common that it can arise in the frozen outskirts of a star system, simmering in the dark beneath an icy crust, then what does that say about the universe's capacity for creation? The plumes of Enceladus are an invitation, a sample of a hidden ocean delivered freely to the void, waiting for a future mission to catch it and read its story. Europa's frozen face tells a story of profound turmoil beneath. This moon of Jupiter gleams like a cracked marble, its surface a global labyrinth of dark, intersecting lines etched across brilliant white ice. These fractures speak of a world under immense stress, flexed and heated by the gravitational pull of its giant parent planet. But scattered across this fractured canvas are even stranger features, regions scientists call chaos terrain. Here, the orderly shell shatters into complete pandemonium. Vast areas, sometimes spanning hundreds of miles, look like a colossal pane of ice that was smashed, stirred, and then hastily refrozen. Gigantic icebergs, some the size of cities, appear to have broken free, tilted, rotated, and been locked into a new, jumbled configuration, all while floating in a matrix of refrozen slush. It is a landscape of frozen anarchy, and it holds the key to what lies below. The leading explanation for this chaos is as dynamic as the features themselves. Europa is not a solid ball of ice. It is a layered world with a global, salty ocean perhaps 60 miles deep, sealed under an ice shell 10 to 15 miles thick. The heat generated by Jupiter's relentless gravitational kneading does not just keep this ocean liquid, it likely creates turbulence. Warmer plumes of water may well up from the ocean floor or from the boundary between the rock and the water, carrying heat toward the icy ceiling above. When these buoyant parcels of warmth reach the bottom of the ice shell, they can melt it from below. Imagine a frozen lake in winter, but instead of the cold coming from the air above, a pocket of warmth suddenly blooms against the underside of the ice. The ice above this thermal hotspot weakens, fractures, and potentially collapses. The once solid crust becomes a slurry of ice blocks adrift in a temporary meltwater lake, suspended within the shell itself. As the heat pulse passes or the water refreezes, this chaotic slurry solidifies, leaving a permanent scar of jumbled terrain on the surface. Some models go even further, suggesting entire shallow lakes might exist for millennia, trapped between the ocean below and the cold surface above, creating a complex, layered aquatic world within the ice. This geological violence is not a sign of a dead world, but of a spectacularly active one. The chaos terrain is a window into the energy of Europa's hidden sea. It suggests the ocean is not a still, dark pool, but a churning engine capable of reshaping its own icy roof. For scientists seeking life, this is revolutionary. These processes could act as a natural elevator, transporting material from the potentially habitable ocean, with its essential chemistry and possible energy sources, up through the ice and depositing it on the surface. Future missions might not need to drill through miles of ice. They could land in a chaos region, scoop up the freshly deposited, jumbled ice, and find within it the frozen fingerprints of whatever swims in the abyss below. Europa's chaotic scars are therefore a map and a message, a direct testament to the powerful, life-giving forces at work in the darkness, and a promise that its deepest secrets may be lying in plain sight, waiting on the surface. The solar system's current arrangement feels almost too perfect, a neat progression of worlds from the sun outward. Yet this very orderliness is what hints at a profound disruption in our past, a cosmic crime scene with a missing body. The spacing between the planets follows a curious mathematical pattern known as the Titius-Bode law, a rough rule that predicted the orbits of Uranus and the asteroid belt before their discovery. But for this pattern to hold, there appears to be a gap, a silent orbit where a world should be between Mars and Jupiter. While the asteroid belt now occupies that zone, it is not a single planet but a field of fragments, leading to a compelling and dramatic hypothesis. What if a planet once did form there, only to be utterly destroyed in the solar system's violent youth? This idea of a lost world, sometimes called Planet V, suggests a Mars-sized body that met a cataclysmic end, its remains scattered as the asteroids we see today. The gravitational fingerprints of this event could even be written into the odd, pockmarked landscapes of the inner planets, potentially explaining ancient, basin-forming impacts. This theory paints a picture of our early neighborhood not as a serene nursery, but as a demolition derby where entire worlds could be born and then shattered. But the mystery of missing planets extends far beyond the asteroid belt into the realm of giants. Sophisticated computer simulations of how our solar system evolved tell a story of profound instability. They suggest that after the planets formed, their orbits were not fixed. Jupiter and Saturn, the two largest bodies, likely migrated inward and then outward in a complex gravitational dance. This grand migration would have acted like a cosmic wrecking ball, destabilizing everything in its path. The current, strangely spaced orbits of Uranus and Neptune, along with the peculiar, tilted paths of countless small objects in the distant Kuiper belt, are incredibly difficult to explain starting from a calm, orderly beginning. The models reveal a startling solution. The best way to arrive at the solar system we see today is to start with one more giant planet, a fifth gas giant, perhaps similar in size to Uranus or Neptune, may have once orbited between Saturn and Uranus. During the chaotic reshuffling caused by Jupiter and Saturn's migration, This lost world would have been violently ejected, hurled by gravitational slingshot into the interstellar void to become a permanent rogue, forever wandering the darkness between stars. This ghost planet hypothesis reshapes our entire understanding of the solar system's infancy. It was not a quiet, stable place. It was a crowded and chaotic construction site where gravitational tugs between massive, young planets dictated a brutal survival of the fittest. The ejection of a giant planet would have been an event of unimaginable energy, scattering comets from the outer solar system inward in a great bombardment, and leaving the surviving worlds on their peculiar, tilted paths as a permanent record of the trauma. This idea forces us to look at the distant, icy bodies of the Kuiper belt not as simple leftovers, but as forensic evidence. Their clustered, oddly inclined orbits are like blood spatter on a wall, patterns that allow celestial dynamicists to reverse engineer the crime. If a planet was indeed lost, what traces did it leave behind in its wake? And more hauntingly, how many other such rogue worlds, born in our sun's family but exiled in that ancient turmoil, are now drifting silently through the galactic night, carrying with them the lost history of our own origins? This search for a missing giant is ultimately a search for our own chaotic birth certificate, written in the gravitational language of orbits. The very substance that defines our world, the oceans that cradle all known life, arrived here as a mystery. Earth is a water world, a brilliant blue oasis in the cosmic dark, yet its formation in the hot inner solar system should have created a dry, rocky desert. Water, composed of volatile hydrogen and oxygen, should have been boiled away by the young sun's fierce radiation before it could ever condense onto our infant planet. So where did it all come from? The origin of Earth's water is one of the most fundamental puzzles in planetary science, and the answer is written in the atoms of every drop. By studying the isotopic fingerprint of hydrogen in our water, scientists can compare it to potential sources across the solar system. Water from different regions carries a subtle chemical signature, a specific ratio of normal hydrogen to a heavier form called deuterium. When we compare Earth's water to that found in comets from the distant Oort cloud, the signatures often do not match, suggesting these icy wanderers from the outer dark were not the primary delivery service. The plot thickens when we look closer to home. Some asteroids, particularly a type known as carbonaceous chondrites found in the outer asteroid belt, have water with a deuterium ratio that aligns much more closely with our own. This points to a dramatic and violent chapter in Earth's history, the Late Heavy Bombardment. During this period, roughly 4 billion years ago, the inner solar system was pummeled by a torrent of incoming objects. The theory suggests that water-rich asteroids, sometimes called cosmic aquifers, rained down upon our young, molten world, depositing their precious cargo and filling the basins that would become our oceans. Yet this cannot be the whole story. Our planet itself is a geologically active vessel. As the primordial Earth cooled and its crust solidified, immense volcanic outgassing from the mantle released vast quantities of water vapor trapped within the rock itself, which then condensed into the first true atmosphere and fell as rain. The current scientific consensus is that we have a mixed inheritance. A significant portion likely came from local asteroids during the bombardment, while another substantial fraction was always here, locked in the minerals of the planet from its very accretion, later released by its fiery interior. This duality transforms our understanding of planetary birth. It suggests that water, the essential ingredient for life, may be a surprisingly common commodity in rocky worlds. If Earth's oceans are a blend of native water and celestial imports, then any planet forming in the so-called habitable zone of its star might also accrete water-rich material or retain its own volatile compounds. This mystery, therefore, ripples far beyond our own shores. It directly informs our search for other ocean worlds, suggesting that the conditions for a blue marble might not be a rare cosmic accident, but a potential feature of planetary formation itself. Miranda presents a face only a planetary scientist could love, a world that looks utterly shattered and haphazardly glued back together. Orbiting Uranus, this moon is a geological mosaic, a chaotic patchwork where three distinct types of terrain collide in jarring contrast. Vast, rolling plains scarred with ancient craters sit abruptly next to regions of intense, parallel grooves and ridges, which themselves border colossal, angular zones of canyons and cliffs. The transitions between these landscapes are not smooth. They are stark, linear boundaries, as if different geological eras were sliced apart and sutured onto a single, small world. The most breathtaking of these features is Uranus, a cliff face scientists believe could be 12 miles high, the tallest known precipice in the solar system. If you stood at its edge, the drop would be over 20 times deeper than the Grand Canyon, a sheer plunge into shadow. This is not the gentle weathering of a quiet, frozen moon. This is the signature of planetary trauma on an epic scale. The leading theory to explain Miranda's fractured face is as dramatic as it appears. In the distant past, Miranda may have been shattered. A colossal impact with another object could have blown the moon apart, scattering its pieces into a temporary ring around Uranus. Over time, gravity would have drawn these fragments back together, but the reassembly would have been messy and incomplete, leaving a jumbled, layered world with its internal structure scrambled. This catastrophic disruption and reaccretion would account for the bizarre juxtaposition of terrains and the extreme tectonic features like Uranus, which could be a fault scarp from the moon's final, violent compaction. Yet there is an alternative, perhaps even more intriguing, explanation. Miranda's orbit is not perfectly circular, and in the past it may have been locked in a gravitational dance with other Uranian moons, a state called an orbital resonance. This rhythmic tug of war with a sibling moon could have stretched and squeezed Miranda's interior, generating intense tidal heating. This internal warmth, now long gone, might have powered massive geological upheaval, melting parts of its icy interior and driving global-scale tectonic cracking and resurfacing from within, before the moon eventually froze solid in its current grotesque configuration. Miranda's true power as a mystery lies in its defiance of expectation. It is a small, cold moon, a place where geological activity should have ceased billions of years ago. Instead, it screams of a past filled with either unimaginable violence or powerful internal forces. Its jigsaw puzzle surface challenges our simple models of how moons age and evolve, proving that size is no guarantee of a quiet history. It forces us to ask, if a modest moon like Miranda can hold such a violent secret, what other stories of fracture and rebirth are written on the countless other small, icy bodies orbiting in the darkness of the outer solar system? Jupiter's Great Red Spot is a monument to endurance in a universe of constant change. This colossal, swirling tempest, an anticyclone wider than our entire planet, has been churning in the Jovian atmosphere for at least 190 years and possibly for several centuries before that. It is a permanent hurricane, a fixed point in the chaotic cloud bands of the solar system's largest world. On Earth, even the most powerful storms are fleeting. They draw energy from warm ocean waters and are quickly torn apart when they encounter land or cooler seas. Jupiter presents no such obstacles. There is no continental coastline to break the storm's momentum, no cool surface to sap its strength. Instead, the Great Red Spot is a self-sustaining atmospheric engine, powered from below by the immense heat still radiating from Jupiter's formation and shaped by the planet's ferocious jet streams. These winds create a vertical shear, a difference in wind speed with altitude that helps stabilize and contain the vortex, preventing it from simply dissipating into the surrounding chaos. It even feeds on smaller storms, absorbing their energy like a celestial predator to maintain its fury. Yet this ancient storm is not immutable. For decades, telescopic observations have recorded a slow but steady change. The spot is shrinking. Once large enough to swallow 3 Earths side by side, it is now perhaps only 1 Earth in diameter. Its iconic brick red color has also faded and shifted at times, becoming a paler salmon hue, possibly due to changes in the chemical compounds being upwelled from deeper atmospheric layers. These transformations pose a profound question: is the Great Red Spot dying, or is it merely entering a new, unknown phase of its multi-century life cycle? The storm's longevity offers a unique laboratory. By studying its mechanics, how it spins, how it interacts with its environment, and how it conserves energy, scientists can build models for weather on all gas giants. This is not just about one storm on one planet. It is about understanding a fundamental type of atmospheric behavior that can only exist on worlds without a solid surface. The Great Red Spot teaches us that stability can emerge from chaos, and that a storm can become a permanent landmark, a witness to centuries of solar system history whose final act has yet to be written. Our solar system's orderly architecture holds a subtle flaw, a misalignment that challenges the very story of its birth. The Sun itself, the anchor of our entire planetary family, spins on a tilted axis. Its rotational pole is offset by about 6 degrees from the average orbital plane of all the planets, as if the heart of the system is leaning slightly askew. This is deeply puzzling. According to our standard models, the Sun and its planets should have formed together from a single, flat, spinning disk of gas and dust. Everything that coalesced from that disk, from the central star to the outermost specks of ice, should share the same fundamental orientation, the same spin direction, like a giant, harmonious carousel. The Sun's tilt breaks that symmetry. It suggests that after the planets had formed and settled into their neat, coplanar orbits, something came along and gave the Sun itself a gentle, persistent nudge. One of the most compelling explanations reaches back into a lost chapter of our star's life. Our Sun was not born in isolation. It formed within a dense cluster of sibling stars, all emerging from the same stellar nursery. In that crowded early environment, a close gravitational encounter with a passing star could have exerted a torque on the young solar system. This cosmic bump might have tilted the entire protoplanetary disk just a fraction, leaving the Sun's spin axis slightly misaligned with the orbits of the worlds that grew within it. It is a ghostly fingerprint of a long-lost stellar neighbor, a fleeting interaction billions of years ago that left a permanent mark on our home. Yet there is another, more contemporary suspect lurking in the theoretical shadows. The hypothetical planet 9, a massive world proposed to orbit far beyond Neptune, could be the culprit. If it exists, its immense gravity, acting over billions of years, could gradually torque the entire solar system, slowly pulling the Sun's axis of rotation out of alignment with the planetary orbits. This would be a staggeringly slow process, a gravitational whisper accumulating into a measurable tilt over eons. This mystery is far more than a celestial curiosity. The Sun's lean speaks directly to the distribution of angular momentum, the spin energy, during the system's formation. It forces astronomers to ask where that original spin went and how it was transferred or disrupted. Solving it requires us to peer into the chaotic nursery where stars are made, to understand the dynamic interactions that are erased by time but may leave subtle architectural clues behind. This slight tilt is a quiet message from the dawn of our existence, a clue that our solar system's story may include chapters of stellar companionship and gravitational intrigue we are only beginning to read. This orderly drop into emptiness is known as the Kuiper Cliff. Beyond a distance of about 50 astronomical units from the Sun, the expected population of small, icy worlds plummets. It is as if our solar system, after a vast and bustling neighborhood of frozen objects, simply ends at a cosmic fence. This is deeply puzzling because our models of planetary formation, suggest the primordial disk of material that built the planets should have extended much farther, fading gradually into a sparse field of icy remnants. Such a sharp boundary implies something dramatic happened here, a story written in the absence of objects. One compelling possibility is that this cliff is a fossilized edge, a relic of the Sun's birth within a crowded stellar cluster. A close pass by another young star in that ancient nursery could have gravitationally sheared off the outer reaches of our protoplanetary disk, stealing away the material beyond a certain point and leaving behind this stark frontier. It would be a permanent scar from a stellar encounter billions of years ago, yet there is another, more tantalizing explanation whispering from the darkness. The gravitational influence of a still undiscovered planet, perhaps the size of Mars or even Earth, could be responsible. Such a world, orbiting in the profound cold far beyond the known Kuiper belt, could have swept its orbital path clear over eons, its gravity either ejecting smaller objects or herding them into specific, distant orbits we have not yet surveyed. This hypothetical shepherd planet would be incredibly difficult to spot, a dark, cold sentinel reflecting almost no sunlight, its presence betrayed only by the empty space it seems to guard. Of course, we must also confront the possibility that the cliff is an illusion of our own making. Our telescopes are peering to the very limits of their capability at these distances. Objects become exponentially fainter and darker the farther out they are. What we perceive as a sudden edge might simply be the point where most objects shrink below our current threshold of detection, a gradual fade into invisibility rather than an actual void. Unraveling this mystery is not just about cataloging distant ice. It is about mapping the true borders of the Sun's gravitational dominion and reading the final chapter of our solar system's construction. Is the Kuiper Cliff a sign of a violent past, a marker for a hidden world, or a trick of the light? The answer defines the very shape of our home in the cosmos. While some moons are frozen worlds, one burns with an inner fire. Io, a moon of Jupiter, is a landscape of perpetual chaos, the most volcanically active body in our entire solar system. Its surface is a tortured canvas of yellow, orange, and red, painted by vast flows of molten sulfur and silicate lava. Hundreds of active volcanoes constantly erupt, spewing plumes of gas and dust hundreds of miles into its thin atmosphere, and lava fountains can be seen from space, reshaping the very ground in real time on a geological scale. This ceaseless violence is not driven by radioactive decay in a core, as on Earth, but by a relentless gravitational tug of war. Io orbits Jupiter in a precise lockstep with its neighboring moons, Europa and Ganymede. For every one orbit Ganymede completes, Europa completes 2, and Io completes 4. This resonant rhythm means that with every circuit around Jupiter, Io gets repeatedly and powerfully stretched and squeezed by the combined gravity of the giant planet and its siblings. This tidal flexing generates immense friction deep within Io's rocky interior, melting it with a heat so intense it can power planet-wide volcanism. We understand this engine well, yet the details of the inferno remain elusive. Predicting exactly which of Io's countless volcanoes will erupt next is nearly impossible, a complex puzzle of subsurface plumbing and stress release. Furthermore, scientists debate the very structure of the Moon's molten heart. Does Io possess a global magma ocean, a seething sea of rock just beneath its crust, or is its mantle merely a thick, partially molten sludge, with pockets of melt feeding specific volcanic hotspots? Each model explains some observations but struggles with others. This world of fire, standing in stark contrast to the icy oceans of Europa and Ganymede, is a breathtaking natural laboratory. It showcases the incredible power of tidal heating, a process that can turn a cold, rocky body into a furnace. Studying Io gives us critical insights into the extremes of planetary geology, helping us understand the possible fates of exoplanets that orbit perilously close to their host stars, worlds that might be similarly stretched and melted by gravitational forces. Iowa's relentless eruptions are a vivid demonstration that a world does not need to be near the sun to be scorching. It simply needs to be in the right or wrong gravitational dance. Even on a world of fire, frozen secrets can endure. Mercury stands as the solar system's ultimate paradox, a scorched planet where water ice survives. This world, orbiting closest to the sun, endures daytime temperatures that can soar past 800 degrees Fahrenheit, hot enough to liquefy lead. Yet at its poles, deep within craters whose rims cast permanent shadows, the sun's light has not shone for billions of years. In these profound cold traps, where temperatures plummet to hundreds of degrees below zero, radar signals from Earth have revealed the unmistakable signature of reflective deposits, water ice hiding in the eternal night. The very existence of ice on Mercury forces a complete rethinking of planetary boundaries. How did water, a volatile substance, arrive and persist on a world that is essentially a baked rock? The leading explanation is a celestial delivery service over eons. Comets and water-rich asteroids wandering in from the outer solar system have pummeled Mercury throughout its history. When these icy travelers struck, most of their water would have instantly vaporized in the immense heat of impact and been lost to space. But a precious fraction, if it landed within the polar regions and was thrown into the permanent shadows of a crater, could have found a sanctuary. There, in the unyielding cold, any water molecule that found its way in would freeze solid and remain, accumulating over billions of years like cosmic snowfall in a bottomless freezer. This alone is a stunning revelation, proving that no world is a simple monolith of temperature, but the mystery deepens significantly. When NASA Messenger spacecraft mapped these dark craters, it found the ice was not pure. It was curiously patchy, and in many areas it was covered by a layer of unusually dark material. This dark blanket appears to be a complex mix of carbon-rich organic compounds. The presence of this tarry substance alongside the ice is perhaps even more puzzling than the ice itself. It suggests that the comets and asteroids that delivered water to Mercury also delivered the basic chemical ingredients for life. These organic compounds, once deposited in the shadows, may have undergone a slow, cold chemistry, processed by the faint, relentless bombardment of cosmic rays over geologic time. This transforms Mercury's polar vaults from simple freezers into natural archives. They are time capsules preserving a record of the water and organics that have rained down on the inner solar system since its infancy. Each dark patch is a page in a chemical history book we are only beginning to decipher. What specific molecules are present? Do they hint at the composition of the ancient comets that helped seed the inner planets? Could similar shadowed ice and dark organics exist in polar craters on our own moon? Mercury's hidden ice teaches a humbling lesson that the conditions for preserving the raw materials of life are not exclusive to the warm, wet worlds. They can exist in the most extreme environments, in the deepest shadows of the hottest planets, waiting in the cold and the dark for their story to be told. Saturn's rings are a masterpiece of cosmic impermanence. Those breathtaking bands of ice and rock, so iconic they define the planet itself, are not ancient monuments but fleeting spectacles. Current research suggests they may be a surprisingly recent addition to the solar system, perhaps forming only 100 million years ago when a wandering comet or an icy moon ventured too close to Saturn and was torn apart by immense tidal forces. This celestial debris, captured in orbit, began the slow dance that created the rings we see today. Yet this dance is far from over. The rings are a hive of constant dynamic activity. Cassini's close observations revealed mysterious dark features called spokes. radial shadows that streak across the rings like the spokes of a giant wheel, appearing and vanishing over hours. Their origin remains one of the ring system's most captivating puzzles. They may be clouds of fine, electrostatically charged dust, levitated above the ring plane by strange interactions with Saturn's powerful magnetic field, acting like a celestial etch-a-sketch that draws and erases itself with invisible forces. Even more profound is the silent rain. Ring particles are constantly tugged by gravity and bombarded by micrometeoroids, sending a slow, steady drizzle of icy material down into Saturn's upper atmosphere. This process means the rings are actively dissipating, losing mass. Scientists estimate that in another few 100 million years, this glorious structure may fade from view entirely, leaving future astronomers to wonder at the blank space where a wonder once spun. We are therefore witnessing a transient phase in Saturn's life, a brilliant but ephemeral adornment. Studying this evolving system is like watching the life cycle of a circumstellar disk in fast forward. Every collision, every gravitational nudge, every mysterious spoke teaches us about the fundamental physics that shaped not just Saturn's jewelry, but the protoplanetary disks that gave birth to all the planets. Their fleeting nature asks a haunting question: what other majestic, temporary structures have graced our solar system in the deep past, only to vanish without a trace before we ever looked up? Iapetus is a cosmic yin and yang, a perfect sphere split into night and day. Orbiting Saturn, this moon presents one of the most visually striking puzzles in our solar system. One hemisphere is a deep, dusty black, the color of fresh asphalt, while the opposite side gleams a brilliant, reflective white, as bright as freshly fallen snow. This is not a trick of shadow or a temporary stain. It is a permanent global dichotomy, a world with two faces. The leading explanation for this bizarre coloring involves a celestial game of dust and ice, orchestrated by another of Saturn's distant moons. Far beyond Iapetus orbits Phoebe, a dark, irregular moon that circles in the opposite direction to most of Saturn's other satellites. Phoebe is likely a captured object from the outer solar system, coated in a layer of dark, carbon-rich material. Micrometeoroid impacts constantly blast this dark dust off Phoebe's surface, creating a faint, inward-falling ring of debris. As Iapetus plows through this tenuous cloud on its journey around Saturn, the dark particles pepper its leading hemisphere, the face that is always forward in its orbit, like bugs on a windshield. This alone would create a dark front, but the story does not end there. The physics of light and heat take over. The newly darkened surface absorbs more sunlight, causing it to warm slightly. This subtle warming is enough to trigger a runaway thermal process on a world where water ice is the bedrock. The slightly warmer, dark areas cause any buried water ice to slowly sublimate, turning directly from solid to vapor. This water vapor then migrates across the moon's surface, seeking colder regions. It eventually recondenses and freezes onto the bright, cold trailing hemisphere and the frigid poles, further whitening those areas. Over eons, this process creates a stark, self-reinforcing segregation, a global feedback loop where dark gets darker and bright gets brighter. Yet, as elegant as this theory is, Iapetus guards more secrets. Encircling its equator, precisely along the dividing line between light and dark, runs a bizarre mountain range, a ridge of peaks that in some places soars 12 miles high. This equatorial ridge makes Iapetus look like a giant walnut or a cosmic sewing thimble. Its origin is a complete enigma. Did it form from a rapid spin early in the moon's history, causing material to pile up at the equator before the world solidified? Could it be the remains of a ring system that collapsed onto the surface? Or is it a tectonic scar from a time when Iapetus's interior shifted and its crust buckled? The ridge and the two-toned surface may be linked, perhaps through the same thermal processes that drive the ice migration. but no model fully explains this precise, gargantuan belt of mountains. Iapetus, therefore, is more than a curiosity. It is a profound lesson in planetary interdependence. Its appearance is not solely a product of its own geology, but a testament to the invisible threads that connect a system of moons. A distant, dark wanderer like Phoebe can, through nothing more than a gentle rain of dust, dictate the climate and color of a world millions of miles away. It shows us that no planet or moon is an island. Each is a canvas upon which the entire solar system can paint its story. Ganymede holds a secret power no other moon can claim. Beneath its icy crust, this world generates its own magnetic field, a protective bubble of invisible force that makes it more like a planet than a mere satellite. This is not a simple reflection of Jupiter's immense magnetic influence, but a field born from within, likely created by the churning of a molten, iron-rich core. It is a tiny, self-contained dynamo whirring away in the dark. For a world of its size, this is profoundly unexpected. Ganymede should have cooled off and solidified eons ago, its internal fires long since extinguished by the relentless cold of space. The persistence of a liquid, convecting core capable of powering a magnetic field for billions of years is a thermal mystery. Where is the heat coming from to keep this engine running? The answer likely lies in its relationship with Jupiter. The gravitational pull of the giant planet constantly flexes Ganymede's interior, a process called tidal heating. This internal stretching generates friction, and friction creates warmth. In the past, Ganymede may have been locked in even more intense gravitational dances, or orbital resonances, with its neighboring moons Europa and Io, which would have pumped far more heat into its core. This complex thermal history, a saga of gravitational nudges and orbital shifts, is the key to understanding how a frozen world can hide a molten heart. The result of this hidden dynamo is a scene of invisible complexity. Ganymede's personal magnetic field exists entirely within the vast, crushing magnetic environment of Jupiter. This creates a unique and turbulent zone scientists call a mini-magnetosphere. The two magnetic fields interact, merging and breaking apart in violent events known as magnetic reconnection, generating shimmering auroras around Ganymede's poles that flicker not from a sun, but from this celestial electromagnetic tug of war. This discovery fundamentally rewrites what we know about icy moons. It proves they are not inert balls of ice and rock, but can possess intricate, layered interiors with active, planet-like processes. Ganymede's silent, internal dynamo challenges every assumption about how mid-sized worlds evolve, suggesting that beneath a frozen exterior, the fires of creation can still burn. Mars hides its secrets in subtle, seasonal whispers. Across its steep crater walls and canyon slopes, dark, finger-like streaks emerge when temperatures rise, slowly lengthening downhill before fading away with the cold. These are the recurring slope lineae, transient stains that paint a tantalizing and contentious mystery. When first discovered, their appearance screamed one thing: liquid water. They looked exactly like what you would expect from damp soil or a thin trickle of brine seeping from the ground, a thrilling suggestion that liquid water might still flow on the surface of Mars today, even if just for a brief season. The implications were staggering, pointing to potential near-surface aquifers or melting ice, and dramatically raising the prospects for modern microbial habitats. But Mars is a world that specializes in cosmic illusions. As orbital instruments stared with greater scrutiny, the simple water story began to evaporate. High-resolution observations revealed these streaks often begin at a point, not a seepage line, and their growth patterns sometimes better match the behavior of dry, granular flows. Imagine dark sand or dust clinging to a steep dune. As the sun warms the slope, a thin layer of frost sublimates, or perhaps the grains themselves undergo a subtle change in electrostatic properties, causing them to suddenly loosen and cascade downhill, carving a dark track as they go. This dry avalanche hypothesis gained traction, explaining the features without needing a single drop of liquid water. Yet the debate is far from settled. Some spectral data from these regions hints at the presence of hydrated salts, minerals that can pull water vapor from the incredibly thin Martian atmosphere and temporarily hold it as a brine. This could create a tiny amount of dampness within the soil, just enough to darken it and perhaps lubricate a flow, a process more like a slow, salty ooze than a stream. The scientific conversation now lives in this fascinating gray area. Are we seeing the last desperate flows of a dying world's water, or simply the restless shifting of its ancient, desiccated sands? This puzzle is a masterclass in how our understanding of other planets evolves. A compelling first impression gives way to more complex, ambiguous data, forcing us to question our own Earth-centric assumptions. Solving it requires more than better cameras. It demands a new physics for an alien environment, where the rules of granular flow, atmospheric chemistry, and subsurface thermodynamics intertwine in ways we are only beginning to model. The truth of these dark streaks will ultimately rewrite a key chapter in the story of Martian water, telling us whether the red planet's surface is truly, completely dry, or if it still holds onto the faint, damp heartbeat of a more hospitable past. The solar system's most profound mysteries are not always those we have studied for centuries, but those that arrive unannounced from the depths of interstellar space. In October of 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint, fast-moving point of light tracing a path that could only mean one thing: it was not from here. This was Oumuamua, the first confirmed visitor from another star system. Its trajectory was a hyperbolic arc, a cosmic slingshot that meant it was merely passing through, never to return. In the frantic weeks of observation that followed, a portrait of profound strangeness emerged. Measurements of its brightness revealed it was tumbling, and the extreme variations in that light suggested an object with a shape unlike anything we see in our own asteroid belt. Oumuamua appeared to be highly elongated, perhaps 10 times longer than it was wide, a shape reminiscent of a cosmic cigar or a flattened pancake. This alone was bizarre, but the real puzzle came from its motion. As it sped away from the sun, it exhibited a slight but undeniable non-gravitational acceleration, a tiny push that could not be explained by the gravity of the sun or planets alone. For comets, such a push is common, caused by outgassing, as sunlight vaporizes ice and the escaping jet of material acts like a gentle rocket engine. Yet Oumuamua showed no visible coma, the fuzzy cloud of gas and dust that surrounds an active comet. It was a dark, silent rock, apparently accelerating with no visible exhaust. This contradiction launched a firestorm of scientific speculation. Some proposed it was a fragment of a Pluto-like world, a shard of nitrogen ice from a distant planetary collision, slowly eroding and providing an invisible thrust. Others suggested a hydrogen iceberg, a chunk of solid molecular hydrogen that could sublimate in sunlight without leaving a dusty trace. Each idea stretched the boundaries of known planetary science, attempting to explain the behavior of an object forged in a star system utterly unknown to us. The most provocative and least likely hypothesis ventured that its shape and acceleration could be consistent with a very thin, lightweight object, like a discarded light sail from an advanced civilization. While astronomers overwhelmingly favor natural explanations, the very fact that such a speculative idea had to be seriously discussed underscores just how deeply Oumuamua challenged our understanding. Its true nature remains locked within that tumbling, dark shape, now receding forever into the void. This brief visitor accomplished one monumental thing: it shattered the illusion of isolation. Our solar system is not a closed ecosystem. It is a harbor in a galactic sea, constantly traversed by ancient relics from other suns. Oumuamua was a messenger, and its message was clear. We know almost nothing about the population and properties of the countless objects traveling the dark lanes between stars. Its passage was a call to prepare our telescopes and our minds for the next interstellar interloper. For when it comes, we must be ready to learn its story before it, too, vanishes back into the night. Deep within the asteroid belt, the dwarf planet Ceres holds a mountain that should not exist. Rising 3 miles high from an otherwise smooth, cratered plain, Unanswered stands in stark, lonely defiance. This is no ordinary mountain, it is a cryovolcano, a geological phenomenon that speaks of a world that is far from dead. Unlike the fiery peaks of Earth or Io, a cryovolcano erupts with a cold fury, spewing a salty slurry of water, mud, and ammonia ice, a frigid lava that oozes and freezes, building a mountain not from rock but from frozen brine. The existence of such a feature on Ceres is a profound shock. This is a small world, only about 600 miles across, a body that should have lost its internal heat and frozen solid billions of years ago. So what force could possibly drive a frozen volcano to erupt in the recent geological past, perhaps within the last few 100 million years? The answer may lie in a hidden ocean, or at least the ghost of one. Scientists believe Ceres has a differentiated interior, meaning it's separated into layers with a rocky core and a thick mantle of water ice mixed with salts. As this subsurface layer slowly freezes over eons, the expanding ice can create immense pressure, like a sealed bottle left in a freezer. That pressure needs a release valve, and Unanswered may be that valve, a place where a pocket of antifreeze-rich brine finally bursts through the brittle crust to create a solitary, icy pimple. This is not the only sign of a restless interior. In Iapetus crater, brilliant white spots gleam against the dark gray surface. These are deposits of sodium carbonate, a salt commonly found in evaporative settings on Earth like dried-up lake beds. Their dazzling brightness suggests they are remarkably fresh, not yet darkened by the constant rain of cosmic radiation. They likely formed when another cryovolcanic event, or a major impact, tapped into a reservoir of briny water beneath the crater. The liquid erupted or seeped out, quickly froze, and left behind a salty residue as the water ice sublimated away into space. Together, Unanswered and Iapetus crater paint a portrait of a complex, geologically active dwarf planet. They tell us that Ceres is not a simple lump of rock and ice, but a world with a memory of internal heat and a potentially global layer of briny water, a subsurface ocean that may still exist in pockets today. This transforms our understanding of small bodies. They are not inert fossils, but dynamic worlds capable of surprising, cold-blooded geology. More importantly, it expands the cosmic real estate for potential habitability. Where there is liquid water, salts for chemistry, and a source of energy, even if just the residual warmth of radioactive decay, the basic ingredients for life as we know it can assemble. Ceres whispers that the conditions for biology might not require a warm, sunlit ocean, but could persist in the dark, salty aquifers of a small world, quietly churning in the deep freeze of the asteroid belt. Neptune's journey is not a solitary one. The giant blue world is accompanied by celestial shadows, two vast swarms of asteroids locked in a gravitational embrace, forever leading and trailing the planet in its orbit. These are the Trojan asteroids of Neptune, captured in the stable Lagrange points where the pull of the Sun and the planet perfectly balance. They are not mere rocks in the void, but ancient travelers with a story written on their dark, red surfaces. Their coloration and composition are a profound clue, suggesting they did not form where we find them today. Instead, they appear to be primordial refugees from the distant, icy Kuiper belt, far beyond Neptune's current realm. This presents a stunning narrative of cosmic migration. billions of years ago, as the giant planets shuffled their positions in the grand instability, Neptune likely marched outward from the Sun. During this epic migration, its immense gravity could have swept up these wandering Kuiper belt objects, herding them into the orbital sweet spots where they remain today, frozen in a perpetual gravitational dance. They are celestial hitchhikers picked up during the most turbulent chapter of our solar system's history, yet their very existence raises intricate questions. The exact gravitational mechanics of that capture are devilishly complex to model. Were they gently guided into place over millennia, or violently snared during close encounters? Furthermore, their surfaces are unusually dark and red, much more so than many asteroids in the main belt or even some classical Kuiper belt objects. This suggests a coating of complex organic compounds called tholins, created when simple ices like methane are bombarded by cosmic radiation over eons. But why do these particular captured objects show such a strong signature? Does it mean they originated from a specific, now-vanished region of the primordial disk, a neighborhood with a unique chemical recipe? Or have their surfaces been processed differently during their long, stable residence in Neptune's gravitational wells, sheltered from the collisions that might refresh and brighten other asteroid populations? Each dark red Trojan is therefore a time capsule, a preserved sample of the building blocks that existed in the outer solar system before the great planetary rearrangement. By studying their orbits and inferred compositions, astronomers are reading a fossil record written in gravity and light. They offer a direct, observational test for our models of planetary migration, providing hard evidence of the chaotic ballet that sculpted the orbits of Uranus, Neptune, and countless smaller worlds. These silent companions remind us that a planet's story is never just about the world itself, but about the entourage it collected along the way, a retinue of ancient stones holding the secrets of a journey 4 billion years in the making. Pluto's tenuous shroud of air is a fragile miracle of persistence. Far out where the Sun is a mere brilliant star, this small world somehow holds onto a thin, hazy atmosphere of nitrogen, methane, and carbon monoxide. It should not be possible. Pluto's orbit is a long, stretched ellipse, taking it from the relative warmth of perihelion, when it is slightly closer to the Sun, out to the profound, deep freeze of aphelion. Common sense suggests that as Pluto journeys into that distant cold over its 248-year orbit, its entire atmosphere should simply freeze solid, collapsing as frost onto the surface. Yet it does not. Instead, this delicate envelope breathes, expanding and contracting with the seasons in a dramatic, slow-motion rhythm. Even more bizarre is the temperature structure of this air. On Earth, the atmosphere grows colder as you climb higher. On Pluto, the opposite is true. The thin gases high above the surface are actually warmer than the frozen ground below, an inversion that creates a global thermal blanket, helping to keep the lower atmosphere from completely collapsing. The source of this warmth is a mystery, likely tied to the absorption of the Sun's faint light by the haze particles themselves, a self-heating mechanism that defies our expectations for such a distant, tiny world. The very existence of this dynamic atmosphere points to something crucial. Pluto is not a static ice ball. It is an active world. For the atmosphere to persist, it must be constantly replenished. When the New Horizons spacecraft flew past, it revealed a stunningly complex landscape of towering mountains of water ice, vast plains of frozen nitrogen, and possible cryovolcanoes. This geological diversity suggests that internal heat, perhaps from the slow decay of radioactive elements in its core, or the lingering warmth of its formation, may still be driving processes that slowly release fresh gases from the surface ices. Seasonal cycles also play a profound role. As different hemispheres tilt toward the distant Sun over centuries, vast reservoirs of frozen nitrogen, methane, and carbon monoxide may slowly sublimate, feeding the atmosphere, only to refreeze elsewhere in a global, slow-motion weather pattern. This tiny world's ability to maintain its own sky forces a complete rethink of what defines planetary activity. It proves that size and distance are not absolute barriers to complexity. If Pluto, at the frozen edge of our solar system, can sustain a dynamic atmosphere and changing geology, then countless other small, icy bodies in the darkness of the Kuiper belt and beyond may harbor similar, hidden layers of delicate activity, each with its own whisper-thin breath held against the cosmic cold. Our own moon holds a secret in its silent path, a subtle tilt that protects our skies from constant drama. The moon's orbit around Earth is not a flat circle aligned with our journey around the sun. Instead, it is cocked by about 5 degrees, a small but monumental lean that means the moon usually passes above or below the sun's direct line of sight. Without this inclination, every single new moon would plunge part of Earth into a solar eclipse, and every full moon would be swallowed by our planet's shadow in a lunar eclipse. Our celestial calendar would be a relentless cycle of darkness and fire. This 5-degree tilt is a guardian of normalcy, ensuring eclipses remain breathtaking rarities rather than monthly expectations. But where did this protective angle come from? Its origins are written in the moon's own violent birth. The prevailing giant impact theory suggests a Mars-sized body, often called Theia, struck the young Earth, blasting a cloud of debris into orbit that coalesced into our moon. That colossal collision would have set the moon-forming disk spinning at a wild, chaotic angle relative to Earth's orbit. As the moon coalesced from that debris, its initial orbit was likely highly inclined. Over eons, gravitational tugs from the sun, and perhaps even the lingering influence of other planets during the solar system's chaotic youth, worked to tweak and stabilize that angle to the precise 5 degrees we see today. This process of gravitational sculpting is a delicate dance of forces, one that computer models struggle to replicate perfectly. The exact sequence of nudges and resonances that locked in this tilt remains a puzzle in celestial mechanics. The implications of this slight lean stretch far beyond beautiful eclipses. This stable, tilted orbit is a cornerstone of Earth's own climate stability. A moon with a wildly changing or zero inclination orbit could exert gravitational torques on our planet, potentially destabilizing Earth's axial tilt over time. Our planet's gentle, reliable seasons, the predictable rhythm of spring, summer, fall, and winter, owe a debt to the moon's consistent gravitational hand, a hand guided by that 5-degree tilt. It is a profound reminder that the most crucial features of our homeworld are often the result of ancient accidents and precise gravitational fine-tuning. The moon's tilted path is a fossil of cosmic violence preserved by gravitational whispers that quietly orchestrates the stability of our days and the spectacular rarity of our eclipses. Even the grandest structures begin with the smallest architects. Deep within the shimmering expanse of Saturn's ring, a population of tiny sculptors is at work. These are the propeller moonlets, miniature worlds no larger than a skyscraper, whose subtle gravity carves a unique signature into the icy fabric around them. They do not possess enough mass to sweep a clean, dark gap like the larger shepherd moons. Instead, their gravitational pull is just strong enough to coax the surrounding ring particles into a peculiar, dual-armed shape that from afar looks exactly like a vintage airplane propeller, earning them names like Blériot after aviation pioneers. These are not static sculptures but dynamic features. As the moonlets orbit Saturn, embedded within the ring itself, their propeller shapes travel with them, constantly forming and reforming in the flow of particles, a wake of gravitational influence made visible. Their existence solves one mystery while creating several more. For planetary scientists, these propellers are a thrilling missing link. They bridge the vast scale between the countless tiny, sand-like ice grains that make up the rings and the fully formed, rounded moons like Enceladus or Mimas. Here, captured in real time, is the very process of accretion, the gathering of material by gravity, frozen at an intermediate stage. We are witnessing moon formation in action, a laboratory experiment on a cosmic scale. But how did these builders come to be? One possibility is that they are the nascent cores of future moons, slowly gathering more ring material around themselves through countless gentle collisions. Another, more dramatic theory suggests they are the surviving fragments of a larger moon that was shattered by a catastrophic impact long ago, its pieces now forever weaving through the debris field of its own destruction. Their movement holds another key puzzle. Observations from the Cassini spacecraft revealed something astonishing. These propeller moonlets appear to be migrating. They are not fixed in their orbits but seem to drift slowly through the rings over time. This motion defies simple expectations, suggesting they are interacting with the ring material in complex ways, perhaps through gravitational torques that exchange momentum with their surroundings. Studying this migration is like watching the opening moves in a celestial chess game that lasts millions of years, a game that dictates whether these objects will eventually coalesce into a proper moon, remain as they are, or be slowly torn apart. Each tiny propeller is therefore a clock, a compass, and a blueprint. It records the passage of time within the rings, points to the forces shaping their evolution, and provides a working model for how all satellites, from these tiny moonlets to the giant moons of Jupiter, may have first taken shape from the primordial disks around their parent planets. In the delicate arcs of ice stirred by unseen dwarfs, we find a microcosm of creation itself. Galileo's first glimpse of Jupiter's moons through a simple telescope shattered an ancient worldview, proving that not everything revolved around the Earth. That single act of curiosity ignited a journey of cosmic exploration that continues to this day, each leap in technology peeling back another layer of mystery from our solar system. The early telescopic era gave us maps of Martian canals and glimpses of distant giants, but these were static portraits full of speculation. The true revolution began when we stopped just looking and started traveling. The Pioneer and Voyager probes were our first emissaries into the deep, dark, brave robotic scouts on one-way journeys. Their grainy images transformed planets from points of light into real worlds, revealing the volcanic fury of Io, the intricate rings of Saturn, and the icy plains of Pluto for the very first time. Each flyby answered fundamental questions about composition and atmosphere, but in doing so, it presented 100 new enigmas. Voyager's grand tour was not a finale, it was an overture. This legacy of discovery was taken up by a new generation of orbiters and landers, each designed not just to visit, but to stay and study. Cassini spent 13 years weaving through Saturn's moons, transforming our understanding of Enceladus from a frozen ball into an ocean world. The Mars rovers have become our robotic geologists, crawling across ancient riverbeds and analyzing rocks grain by grain, turning the red planet's history from a myth into a complex geological saga. Every mission, from Galileo at Jupiter to New Horizons at Pluto, has followed the same pattern, replacing broad mysteries with precise, deeper puzzles. We no longer ask if Mars had water, we ask what specific chemistry existed in its ancient lakes and where that water went. We no longer wonder if the outer moons are active, we measure the composition of their plumes to read the chemistry of hidden seas. This progression reveals a profound truth about science. Knowledge is not a destination but a horizon that continually recedes, inviting us forward. The current fleet of explorers, from the Perseverance rover drilling samples on Mars to the Juno spacecraft mapping Jupiter's deep interior, and the future Europa clipper preparing to fly through a watery moon spray, represents the most sophisticated chapter yet. They are detectives equipped with mass spectrometers, radar sounders, and high-resolution cameras, searching for forensic evidence of past life, internal oceans, and planetary evolution. This historical perspective frames every unsolved mystery not as a failure of understanding, but as the exciting frontier of a continuing adventure. Each unexplained hexagon or vanishing methane plume is a signpost erected by our own curiosity, marking the next question we were clever enough to ask. The journey from Galileo's lens to today's orbital laboratories shows that our place in the universe is not that of passive observers, but of active participants in an epic story of discovery, where every answer unlocks a deeper, more beautiful question about our celestial home. These cosmic puzzles, from the plumes of Enceladus to the ice of Mercury, are not random curiosities. They are threads in a single, magnificent tapestry, woven together by a few profound and recurring themes. First, and perhaps most vital, is the story of water. We find it everywhere, not just as a liquid, but as a sculptor and a sanctuary. It is the hidden ocean churning beneath Europa's ice, the ancient brine that built Oumuamua on Ceres, and the fleeting vapor whispering through the Martian air. Its presence in every state transforms our understanding of habitability, suggesting that the essential ingredient for life is not a rare luxury, but a surprisingly common cosmic commodity, waiting in the shadows of the hottest planets and the hearts of the coldest moons. Equally powerful is the invisible hand of gravity. It is the force that kneads the interiors of Io and Europa, turning rock to magma and ice to a global sea. It is the architect behind the orderly migration of Neptune's Trojan asteroids and the chaotic tilt of Uranus. This gravitational influence extends to the dance of orbits, locking moons into resonant rhythms that dictate their geologic fate and sculpting the very architecture of our system, from the possible ejection of a lost giant planet to the gentle lean of our own moon that guards our skies. Gravity is the quiet composer of this celestial symphony, its melodies written in the spin of worlds and the paths they travel. These forces acted upon a stage set during a period of incredible violence. The solar system's youth was not a placid era of slow assembly, but a time of colossal collisions and gravitational upheaval. The strange tilt of the Sun, the possible destruction of a planet between Mars and Jupiter, and the peculiar orbits of distant icy bodies all point to a chaotic past. This was an age of migration where giant planets shuffled like cosmic furniture, scattering comets, capturing moons, and leaving behind forensic evidence in the form of tilted axes, missing worlds, and captured asteroids. Our current, seemingly stable arrangement is the calm after a storm of unimaginable force, a frozen record of that ancient turbulence, and woven through the themes of water, gravity, and violence is the most captivating thread of all, the persistent whisper of life. The organic-laced plumes of Enceladus, the methane mysteries of Mars, and the dark, tarry blankets over Mercury's ice all point to chemistry complex enough to be a precursor to biology. These are not guarantees but powerful possibilities. They suggest that the conditions for life are not confined to a narrow, sun-drenched band around a star, but can persist in the dark, heated by tidal forces, or in the deep freeze, preserved for eons. Each unexplained chemical signature is a beacon, redirecting our search from mere habitability to active, potential vitality. Seeing these patterns is more than an intellectual exercise, it is a practical guide. Recognizing that tidal heating is a universal engine helps us predict which distant exomoons might hide oceans. Understanding that atmospheric mysteries often stem from interior processes tells us where to aim our instruments. The solar system is a single, interconnected system, and solving one mystery often provides the master key for several others. The quest to understand a storm on Jupiter informs our models of weather on worlds around other stars, and the search for a source of Martian methane could ultimately reveal the history of organic delivery to early Earth. What begins as a collection of bizarre, isolated riddles gradually weaves itself into a coherent and epic narrative, the story of our own home and its place in a universe that is far stranger and far more connected than we ever dreamed. Our solar system is not a museum of static, solved puzzles. It is a living, breathing, and profoundly unfinished story. From the hexagonal hurricane at Saturn's pole to the dark streaks on Martian slopes, from the lonely Cryovolcano on Ceres to the tumbling shape of an interstellar visitor, each mystery we have explored is a testament to a single, humbling truth. We have only just begun to read the first few pages of our own cosmic neighborhood's epic. These are not failures of science, but its very fuel. Every unexplained plume, every tilted axis, every hidden ocean is an open invitation, a direct challenge to our understanding that calls for sharper telescopes, more daring missions, and bolder ideas. The universe feels no need to conform to our expectations, yet our curiosity is the relentless force that slowly, beautifully coaxes its secrets into the light. This journey does not end here. It continues every time you look up at the night sky. That bright dot of Jupiter holds a moon with a subsurface sea. That faint, steady gleam of Saturn is encircled by ephemeral rings that are actively raining into its atmosphere. The red glow of Mars may whisper of ancient rivers or even modern, briny seeps. Let this knowledge transform your view of the heavens from a static tapestry into a dynamic, unanswered question. Which of these 25 mysteries captured your imagination the most? Was it the potential for life in Enceladus's hidden ocean, or the violent, ancient collision that may have knocked Uranus onto its side? Share your thoughts below, and if you are hungry for more journeys into the unknown, subscribe and join us as we continue to explore the deepest wonders of the cosmos. The greatest adventure lies not in having all the answers, but in forever asking the next question. Keep looking up.